So one of the things we're supposed to talk about is density and pressure. And when I say that, I mean we're supposed to talk about it in a kind of a definition kind of way, just like you're supposed to understand what these things are. I don't think I have to spend a lot of time talking about density, but I do think that you have to have an understanding that compressible fluids deal with density differently. Now remember, compressible fluids are gases. Well, non-compressible fluids are liquids. A non-compressible fluid can't be compressed, so that suggests that its density stays relatively unchanged. Density is the mass per unit volume. If I put pressure on a liquid, its volume doesn't change, so its density will stay the same. Now, you guys were able to write out all sorts of stuff about the gas laws. So I saw all the things I would have expected to see, except for a few of you who didn't know them because you didn't study like I suggested. They're not particularly hard. In fact, I think writing all of this out is a bit of a waste of time. Not because studying is a waste of time, but because if you wrote all these out, then you missed the point that there's one law that can do this all just at one time, and that's the combined gas law. It says all of these same things all at once. Now, you should know that this all comes from something else, something that you also learned. But let's just at least start here, because there are some key points here that if you don't remember, you'll get messed up. For one, it doesn't matter what you measure pressure in here, as long as you're consistent between both sides. And it doesn't matter what you measure volume in, but again, you have to be consistent on both sides. It does matter what you measure temperature in. What do you have to use for temperature if you want to use this function? Has to be Kelvin. You can't just use any of our temperature scales. You have to use Kelvin. So now that that's handled, this should make it clear that if you're changing the parameters of gas, that all three of these parameters can change. But it also, if we kept the temperature constant and we increase the pressure on a gas, its volume's going to decrease. It's going to become more dense. So the density of a gas isn't constant. Density of a gas changes depending on the conditions of the gas. One thing that is, I think, left out of your conversation in chemistry has to do with this rule. What is this? Ideal gas law, PV equals nRT. Did anybody learn this in a different way? Did anybody learn PV equals NKT? Okay. So you all have the same kind of shared experience then, where your experience is about number of moles, right? That's your experience? You know, does it not dawn on you that you could say PV over T equals NR? And doesn't this look a lot like that? What this is saying is that these three things together tell you how many molecules of a gas you have. If you know the pressure, volume, and temperature of a gas, that tells you how many moles of the gas there are. Right? That's how they're equal. But if the number of moles of your gas doesn't change, I mean, if you trap a gas in a container and you don't change how many molecules are in there, right? Number of moles is just the number of molecules, right? Remember, a mole is a Avogadro number of molecules. So you know how many molecules there are. So if you know how many molecules there are, these can change all the time, but it never changes how much gas is actually there, right? Now, this next part I hasten to go into with you guys because I don't think you'll understand why I think it's valuable. But I want you to be smarter people. So we're going to do this anyways. Let me get rid of all of this for just a moment. And I want you to think of this for just a second. The units we're going to use for pressure are the pascal. And by definition, pressure is force over area. That's what pressure is. It's the force per unit area, which means this is a Newton per meter squared. That's a pascal. Capital P, lowercase a. It's named after a scientist. It's like a Newton or a joule. How do you measure volume? Go ahead. No, you're thinking pressure. How do you measure volume? Cubic centimeters, cubic meters. Because I have this in meters, I want to talk about volume being in cubic meters as well. Is that okay? Now look at what this is. P times V, which would be pressure, Newton per meter squared, times volume, meters cubed. You guys see that okay? Well, this reduces, doesn't it? What do I get when I reduce this? A Newton times a meter. Does anybody remember what unit that is? It's got a name. Go ahead. It's a joule. Joule is the unit of what? I tell you how many joules you have. What am I telling you? Go ahead. It's energy. It's a unit of energy. I don't know that you understand this, but PV equals nRT explains how energy exists in a different kind of system than you're used to. This is how your car engine works. It's 100% how your car engine works. You don't see it like that because you're not thinking of it the way this is intended. But I want you to think for just a moment. We said that whenever a force is used to move an object, that work is being done. And we are specifically talking about forces on objects. But in your car, you have something called a cylinder. I'm sure you've heard that phrase before. But the cylinder is literally that. It's a cylinder that has a handle on it. And this area gets filled with gas. So that can adjust like a syringe. It can adjust that. Now, what happens in this system is at the start of the cycle, the syringe presses on the gas, making it small. Reduces the volume by applying pressure. But then we suddenly change the temperature. Right? We add energy by igniting the gas in the air. So it gets really, really, really hot. Well, if we make the temperature go up a lot and we don't change the volume at that moment, the pressure is going to go up a lot, right? The pressure goes up a lot, it's going to push on the piston and will push the piston out. Do you understand what I mean by that? So that means the pressure will go down and then the volume will go up. That's what happens in your car. And that's work, right? The pressure times the change in volume does work on the engine. You have a couple of cylinders doing this, and each one of those cylinders is pushing on the motor to turn the motor around. It's just another way of doing work, but we're using gas to do the work instead of individual forces. So pressure in this case is the force part, and the change in volume, that's the displacement part. Now, we tend to not understand this part, so let's take a look at the world. I want to get nice and close to the world. This is supposed to be, the Earth, and I put the white line there to kind of indicate where the atmosphere is, but this is exaggerated. The atmosphere wouldn't look like this. the atmosphere would be much closer to the Earth. It would be, even though it's a couple miles tall, the whole Earth is really, really big. So I am exaggerating the size of the atmosphere. But in chemistry, you learned that one atmosphere is equal to, do you remember how many pascals? It's 101 kilopascals. That means 101,000 pascals. It's a lot. Now, earlier today, we measured the tables. They are 1 meter by 3 meters. Does that make sense? Yeah, so just 1 by 3. How much force is there from the air on the table? I mean, if pressure equals force divided by area, the force on the table from the air should be equal to the air pressure times the area of the table. You have to imagine that if you could contain just the air on this table, put a big cylinder all the way up to the ceiling and go all the way past the ceiling to the top of the atmosphere, that is how much air is pushing down on the surface of the table right now. So when we say that the pressure at sea level, which is where we are, we exist at sea level because we're in Florida, is 100,000 pascals. Well, the table is 3 square meters. So that's 101,000 newtons per meter squared times the area of the table, which is 3 meters squared. That means the force from the air just on the table is 303,000 newtons. Well, I guess we'll finish this tomorrow. So now that it's the beginning of class, the next day, we can come back to this a little bit and maybe not be in as big a hurry as we were yesterday. I do want to remind us that we're talking about the pressure from the atmosphere, which is extreme. So I'm going to kind of zoom in more. And I want you to consider that there's like a column of air stretching from the top of the atmosphere to the ground. And all of that air is experiencing gravity downwards. Now, the ideal gas laws kind of give us a picture of what this must do, right? Probably suggest that with the weight of the air on each layer is probably becoming less dense. Because if we think about it from the standpoint of the air is a gas. And because it's a gas, the stuff at the bottom is probably feeling the most amount of force downwards, and all the stuff above it's pushing down. But the stuff up here is feeling a lot less of that. So the atmosphere is not the same density. It gets less dense the further away from the surface you go. And I think that makes reasonable sense. But right now, my computer is sitting on my desk, and my computer is rectangular-ish. So let's say my computer is rectangular-ish. And it is, I measured it earlier today, and can you just take my word on this one? I don't have to hold a meter stick up to it. Oh, good. It's 20 centimeters on this side, which is 0.2 meters, and 30 centimeters on this side, 0.3 meters. Near the surface of the Earth, the air is pushing down with incredible force on this side of my laptop. being that you guys did this yesterday, can you use our definition of pressure and what I just told you about the size of my laptop, and tell me how much force there is on the top of my laptop? I'll give you a moment. I'll remind you that we are near the surface of the Earth, which means we are experiencing 1 atmosphere of pressure, which is 101,000 pascals. And some change, but we'll just leave it at 101,000 pascals. And again, it's 0.3 meters on one side and 0.2 meters on the other. I'll give you a second. 6060. You sure? It's 60,000? I think you have an extra zero in there. I think it's 6,000. Anybody want to back me up or back? There we go. Now, let's. There's a couple things we can do here. Now, remember, we're talking like this is how much air is stacked up on my laptop going all the way up to the stratosphere. I know there's a roof here, and you're thinking, well, that air can't be helping. Sure it is, because that air is pushing on the roof and it's coming around inside the walls, comes through the door, comes through the windows. The air pressure here is that. So if I take a column all the way up to the stratosphere and try and figure out, well, how much air is there above me? Well, if I just set this equal to mg, this will tell me the mass of air above me. And it's got to be the way it works. So what is the mass of air that's above me, or above my laptop? You just divide it by 9.8. Yeah, go ahead. 618.36. All right, 618 kilograms of air. That's a lot. I don't know that I can lift 618 kilograms of air, but I don't know that you guys know if that's a lot or not. So if you multiply that by 2.2, you'll get the equivalent amount in pounds. And you know about pounds. So if you do that, you get like 1,300 pounds. And although I see a lot of people who work out a lot in here, 1,300 pounds, that'd be a lot for any of you. So the question I have is, Mr. Shelton, this sounds fake, like you're just making this up, right? Because if that were true, how could I ever lift my laptop off the desk if there's 1,300 pounds of force downwards on it? And the short answer is, I don't have to worry about the 1,300 pounds here, because it also means that there's 1,300 pounds here, right? There's atmosphere everywhere, and the pressure from the atmosphere downwards is the same everywhere at this level. So since the pressure is 101,000 newtons per square meter, the force on the top and the force on the bottom are nearly the same because they're the same area. Does that make sense? So how would I ever experience this massive force? Well, I'd have to suction this to the table. Now, you guys, I'm using that word because you guys have an appreciation for what that means. But if I could get the air out from under the table, so there's no air pressure there, well, then yeah, there would be 1,300 pounds of force pushing straight down on the laptop with no force on the bottom. I would not be able to peel it up. And if you've ever been able to successfully seal a suction cup, that's what a suction cup does. Anytime you put a suction cup against the wall, the shape of the suction cup is pretty clear, right? So we have a wall. I'm looking at bewildered faces. Suction cup? I don't know what that is. So you bewildered people. A suction cup is circular, right? It's got it's not particularly hard to envision. It probably looks something like this, with maybe a smaller one of those in the center. So it looks something like that, like a suction cup. But from the side, a suction cup kind of looks like this. Would you agree? Something like that? And there's air in here. So what we do is we push down this way and squeeze out all the air. Now, if the surface is porous, the air gets back in and nothing good happens. So you have to find a surface that will allow for a good seal to be created so the air can't get back in. So, you take your suction cup and look at it and put it on the wall. Or maybe just get it wet with some other source so you don't have to put it on your face and put it against the wall and push the air out. Now, I'm not saying it's going to have 1,300 pounds of force here. Remember, the force experienced depends on the pressure and the cross-sectional area of the suction cup. So if the suction cup is small, it probably is going to have less force. But there's still going to be 101,000 pascals of pressure against the suction cup. And based on the area of the suction cup, we'll determine how much force will be against the suction cup. I bet, even if it's small, like how small of a suction cup are we talking about here? Maybe it's 1.5 centimeters across. So 1.5 centimeters. But let's try and use some reasonable numbers. 1.5 centimeters would mean the whole suction cup would be about that big, 3 centimeters. Does that look like a good sized suction cup? That'd be something small, like you'd hang up something small, like your keys on it. Or do you want a bigger one? But I think you think bigger? Because I'm thinking, what do you have at home? Does anybody have? I have suction cups at home that hold stuff like against the fridge.
In the bathroom.
The bathroom, hold your little cup there with your toothbrush in it, right? Or the things that are in the shower. All right. So maybe it's maybe it's a 4 centimeter one. Is that more the right size? So that'd be a radius of 2 centimeters. So let's do that. Let's say it's a suction cup in the bathroom holding your toothy brush and your soap and all that and your razor. 0.02 meters. We got to find the area of that. And you guys know area, pi r squared. So what is the area of that? Right? If our radius is 0.02 meters. Yes, I know the whole thing with the calculator and the pi and all that stuff. You've got to do the work there. I certainly ain't doing the work. I'm getting my stupid tea. Boy, so very small. 0.0 what?
0.001256.
126?
1256.
56, okay. Meters squared. Boy, it's not very much area. But do we need very much? Remember, the force is going to be the pressure, 101,000 newtons per meter squared times 0.001256. All right, go ahead, lay it on us. What is the force against that suction cup? Say again, loud.
126.920.
Well, I'm just going to go 127, if that's okay. 127 newtons. Again, is that a lot? 127 newtons sounds more reasonable. I divide by 9.8, gives me about 13 pounds, or 13 kilograms. So that's about 28 to 30 pounds of force. Now that's something reasonable. You could probably pull that off the bathroom wall, but I bet it can hold several pounds of stuff in that little cup, which is why it doesn't fall off the wall. Now, be careful. I don't think it can hold really 30 pounds. Remember, it's 30 pounds of force this way, but it's trying to keep stuff from sliding down the wall. That's different, right? So there's a lot of force pushing it against the wall, but, it could slide down. So there has to be some friction there, too. But I'd say that's a lot of normal force, wouldn't you? This is how a suction cup works. And don't get me wrong, I don't think the person who invented the suction cup knew anything about this. But we know things, so we know about this. This is how it works. But I also want you to be clear. That force is acting on you now. It's acting all over your body. It is pushing you in from all sides. And although you don't experience it, you don't feel it, because A, you were born into it, but also your body's evolved to deal with it. In fact, you probably need it. It's the only way you can breathe. You don't pull air into your lungs. You make an area of low pressure, and the external pressure pushes the air into your lungs. A vacuum cleaner doesn't create an area of suction. A vacuum cleaner blows air out the back of the vacuum through the filter. And because it does that, air from the outside is pushed in. I've said it before, physics is about pushing, going from high pressure to low pressure. Now, I do want to try and show you something mathematically, and I know how you all feel about that, and I don't care. You still have to know this. So, is there anybody in here who has done any scuba diving or skin diving? You've done scuba? You've done scuba? Okay. So you'll know a little bit about this, which is good. I can rely on you guys to say, yes, that's true. Or no, Mr. Shelton doesn't know what he's talking about. I have never scuba dived. So let's imagine that we have a pool, okay? And I just want something deep enough where we have some kind of respectable sizing that we can look at. I want to place, or I want you to consider that this, of course, is a non-compressible fluid. Okay? It's a non-compressible fluid. So anything that's a liquid is what we're talking about here. So if water's one is an obvious one to talk about. But like any pool, there's air pressure on the top of that liquid, because we're still here on the earth, so the pressure of the atmosphere is on top of that. People who dive oftentimes have a watch that they can use or a depth indicator to tell them how deep under the water they are. But a depth indicator doesn't actually read the depth of the water. The depth indicator measures the pressure and has a sensor, basically just a force sensor like we have. And the higher the pressure on it, the bigger the force of the water, the deeper it knows you are. Now, as you can imagine, if we look at just this picture, the deeper we go, the more water there is above you that's pressing down on you. So there's something called gauge pressure. Gauge pressure is only accounting for the pressure experienced from the fluid, the liquid that you're under. And gauge pressure is the density of the liquid, the acceleration of gravity, and how deep under the water you are, or how deep under the fluid. Now, a watch or a gauge indicator or a depth indicator measures the pressure and uses this relationship to calculate your depth. However, absolute pressure includes the atmosphere. The gauge pressure does not. The gauge pressure assumes that when you're in the atmosphere, you're like at zero, because that's what you're always under, and it only tells you about what's being added to the pressure that you have. So when calculating pressure, or somebody tells you what the pressure is you're experiencing, you have to ask, are you telling me the absolute pressure, or are you telling me the gauge pressure? They're two different things. Absolute pressure is going to be the gauge pressure plus whatever the atmospheric pressure is at the surface of your liquid. So whatever the atmospheric pressure is here. Now there's a couple things I think are obvious. If you go to the same depth in fresh water versus salt water, you're going to experience more pressure in the salt water than the fresh water. You see why that's probably true? I'm just looking at density here. Salt water is more dense than fresh water. So under salt water, you experience more pressure. G is not going to change very much, but clearly it's linear. You double how deep you go, you double the amount of pressure you experience, which is why there's maximum depth that people can go. And maximum depth that like your watch and phone can take before the force on the phone from the water destroys the phone or destroys the watch. That's why they all have certain ratings for how deep they can go before the seals inside stop holding the water back. Where that force is too much, starts to break into the object. This is not a big deal, but I do want to show you something that I think it'll give you an idea of what's happening for something else we talked about. Consider the fact that our object actually has two depths. The depth at the top of the object is at, and the depth at the bottom of the object is at. And the bottom of the object is deeper than the top of the object. You follow that statement? Right? Because the top of the object is one height below the surface, and the bottom of the object is a different height below the surface. Which means that the top height is experiencing one pressure, but the bottom is experiencing a bigger pressure. Now, this wasn't a big deal when we're in the atmosphere. Like when I was looking at my laptop, I wasn't really thinking too much about the fact that there might be more force here than here. It's technically true because I'm a little deeper in the atmosphere between these two. But come on, really, is there really much of a difference? And what we find is that generally, unless you have big changes, because the atmosphere isn't very dense, it takes big changes in height to get any meaningful change in the force between two spots, because it's based on density. And air is not very dense, like 0.000 something, something, something. So we're talking like not a big change between one height and another. But water's very dense. So a couple of centimeters, couple of meters, big difference in the amount of pressure between the top and bottom of an object. This is why you can compress objects. That could be bad for them if you're one of the objects. Now, at the same time, I want you to walk with me for this just a minute. Can we all agree that if this is a cube, the area of the bottom and the area of the top are the same? So, the pressure at the top would be rho g h1. And the pressure at the bottom would be rho g h2. Make sense so far? We all good? Okay, it's going to get a little complicated. I'm going to make up the positive direction. And I'm noticing that my object is experiencing two pressures, a pressure at the bottom and a pressure at the top. I know things about forces, so I want to convert this to a force on the top and a force on the bottom. And I'm going to say the top and bottom have the same area, A. So the force on the top will be the pressure on the top times the area, right? Because pressure is force divided by area. So pressure on the top times the area. And the force on the bottom is going to be the same. It's going to be the pressure on the bottom times the area. Are we all good? That suggests that the net force from the fluid will be rho g h2a minus rho g h1a. Everybody good so far? Okay, here's what I'm gonna collect some things. I'm noticing rho g is the same, so I'm taking rho g out. And then I have h2 minus h1 all times a. I don't know that you have the wherewithal to see what's in the brackets. If the area is the same, well, h2 minus h1 is just how tall the box is, right? Because h2 minus h1 is just going to be whatever this is. Well, I'm taking the area of the box and multiplying by how tall the box is. Can you see that that's got to be the volume of the box? If you can see that, that should tell you that the buoyant force, which is the difference between these two forces, is rho g times the volume. Buoyant force, although Archimedes didn't know this, but the buoyant force comes from the difference in pressure between the top and the bottom pressures. That's what creates the buoyant force. Now, I chose an object that had a very convenient shape, but this is true for all objects, regardless of their shape. The buoyant force on any object in the water, including you, will be the difference in pressure between the top of your body in the water and the bottom of your body in the water. And that's what buoys any object to the surface. If their weight is greater than the buoyant force, they still sink, because neither of these forces is capable of lifting them to the top. But the buoyant force comes from the difference in pressure between the top and the bottom. I'm going to change gears, okay? I want to talk about something else that you know, but you have no words to describe it. How many of your sprinkler heads in your shower are adjustable? You've got the one that you probably use for some things and one you probably use for others, like washing your hair. Maybe you have a one you like the most, gets the soap out better. And maybe when you're tired, you have a different one that feels good on your back, or when you're cold, maybe. You guys know what I'm talking about? Adjustable stuff. Do you have one that's like you don't use it because it hurts, because the water comes out too hard? Now, I'm trying to bring this up because I think you know things, but you don't always have a way to articulate it. If I gave you a hose, I turn the hose on as much as I can, and I say, squirt your friend over there, and all it is like a regular opening of a hose. Has anybody here? I tried to say you in physics, you're right. If I want to get my friend and all I have is a hose, and I turn the hose on and the water just comes out a little bit, if I want to get them, I put my thumb over the top of it, now I can get them and chase them for as long as the hose will let me. You know things, but remember, physics is about, figuring out, well, how does that work? So although you know this, what's happening here? That's what we're trying to figure out. So this is something called Pascal's principle. And sorry to bore you. And what it comes down to is something about the flow rate of a fluid. The flow rate of a fluid is based on the pressure on the fluid, okay? The flow rate on a fluid is based on the pressure on the fluid. The pressure on a fluid determines the rate that the fluid will flow through a system. So imagine having a large diameter pipe that is reduced to a smaller diameter pipe. And I'm drawing it like this rather than drawing your thumb over it because I want to have something big enough where we can talk about it. But this would be the same thing. This would be what you would have if you had like one of those things that you put on the top of your hose that reduces down the flow rate. It doesn't use your thumb. You can just use your hand now and hold it and point it at people and boosh them right in the face, right? The flow rate of a fluid in a closed system is constant everywhere in the system. And the flow rate is the volume per second of fluid. This is a constant in a closed system. So as water's moving through a pipe, the volume that passes any one location per second stays the same. The volume that passes any one point stays the same. So imagine right here at section 1. There's a volume of fluid here, right? As this fluid passes through the pipe, that volume of fluid passes this point A. The same volume passes by there every second. But the flow rate has to stay the same at A and B. Now you do notice that my volume of fluid has a big surface area, so it's not very long. Well, when I suddenly have a tiny surface area, doesn't it make sense that it's going to have to be much longer for it to be the same volume of fluid? What clearly happens here is the only way we can get the same volume through a smaller place is if the fluid is traveling faster, so that you can move that whole bit of fluid through there faster. And it's really simple. Pascal's principle says the cross-sectional area and velocity at one place has to be proportional to the cross-sectional area and velocity at another. It's kinda, but this is more like conservation of volume. Like the volume stays the same. So when you reduce the size of the opening at the front of the hose, you make the flow rate super fast because it still has to have the same volume passing your thumb at every moment. If you try and cut it off too much, just push your thumb out the way. So up right here. One of the things I didn't say yesterday that I really want to make very clear is this works mostly with non-compressible fluids. And the reason is pretty simple. If a fluid is flowing through a pipe and suddenly you are going to encounter a region where the cross-sectional area changes, the size of the fluid can't change. So if it takes up a certain volume, it's going to take up that same volume whether it's here or whether it's here. And the fluid can't get backed up. It can't get closer together or further apart. So all that can happen is whatever volume of fluid you have has to be the same volume no matter where it is along that travels through the pipe. Now, that explains why the fluid goes faster in some places than in others. That's the first part of it, and that's Pascal's principle. However, there's something else happening here that's going to look way complicated, but I promise you, it's not particularly complicated. It's well within your capabilities. As the fluid moves through the system, there's another principle at work here called Bernoulli's principle. And I have not been looking up how to spell it, and so I have no idea if it's right or wrong, but somebody looked it up and has placed it on the board, so it is the correct spelling. I got it right today, and so far I'm batting 2 for 2. I spelled it right a second time without looking, but that is the actual spelling, and we're going to talk about Bernoulli's principle now. Bernoulli's principle and Pascal's principle are complementary. They work together, but they're used in different ways. So Bernoulli's principle is actually a statement of conservation of energy. That's what it really is. It's a statement of conservation of energy. And what it states is going to look complicated, okay? But when I'm done, please understand, it's not particularly complicated. But it does have 3 things in the equation, which is why I think people think it looks complicated. So here's what it looks like. Bernoulli's principle says, if a fluid is flowing through a system, then a combination of the pressure of the fluid, an expression of gravitational potential energy, and an expression of kinetic energy all sum to be a constant. Now you can clearly see that these things look like kinetic energy, right? 1/2 rho v squared. It's not exactly kinetic energy because it's density, not mass, but we're talking about a fluid, so there's reason to use rho instead of m. But this is an expression of kinetic energy. This is an expression of gravitational potential energy, and this is just the pressure, what we're going to call the internal pressure of the fluid. The word internal here is ornamental. It's just the pressure. What we're saying is the internal pressure of the fluid. As a fluid flows from one place to another, these 3 things sum to be a constant. They sum to be a constant. Let me kind of show you what that means. We have an example above us, right? With this water going through a wide pipe and then going into a narrower pipe, right? And let's say that the fluid is flowing in this direction. So this is VA, and over here is VB. The first thing I want to point out is that if I draw a line through the middle, it looks like the fluid never changes its height. Do you guys see what I'm saying? That in this example, the tube is horizontal, so the fluid stays at the same height the whole time. Yeah, there's some down here that goes up, but there's also some up here that comes down. So the average height of the fluid is the same. Is that okay with you guys? So what we say in this situation is that the pressure at A, the height at A, and the velocity at A, where A is right here, has got to be equal to the pressure at B, the gravitational potential energy at B, plus the kinetic energy at B. Now, again, I said to you guys, this works with Pascal's principle. So in looking at Pascal's principle, we know that VA and VB are different, right? As that liquid goes through the pipe, the cross-sectional area at B gets smaller, so VB is greater than VA. Does that make sense? Now, what does that tell us in Bernoulli's principle? Well, if we look at Bernoulli's principle, this term and this term are the same because the height never changed. Is that okay? But VB increased, right? So that means the kinetic energy of the fluid is greater. If the kinetic energy is greater, that means the pressure had to drop. So when the fluid made it to the other place inside the tube, because the kinetic energy increased and these things have to be equal, the pressure had to drop. So when a fluid travels faster, Bernoulli's principle tells us the internal pressure gets lower. And that's how this works. Bernoulli's principle is a statement of a conservation of values. It just adds pressure as part of the values. Did somebody break it?
Yeah, it's broken. When we got it, it wasn't working.
Who broke it? Who turned it upside down? The first thing we've learned here by looking at Bernoulli's principle is that it speaks to, you can determine how the pressure in a pipe changes based on how fast it's traveling through the pipe. That's the first thing I want to point out. I'm going to point out two other examples of how Bernoulli's principle gets used and what I expect of you for Bernoulli's principle. Way that I think, this is something that I'm not sure you'll be asked about it, but I think all learned people should know about it. And you guys are learned people. A wing isn't shaped like this arbitrarily. Although the shape of wings today is a feat of engineering, it's also a marvel of evolution. So a bird's wing has this shape too. So we're using just a cross-sectional area of a wing to give us an idea about it, but remember, air is a fluid. So air also has to obey Bernoulli's principle. And in many ways, under certain conditions, air also obeys Pascal's principle, even though it's a compressible fluid. So although Pascal's principle is applied to non-compressible fluids, it can also be applied in certain circumstances to compressible fluids, and the flow of air across the wing is one of those. Now this only works when the flow of the air across the wing is relatively slow. That's when Pascal's principle is still in play. When the flow of the air gets too fast, Pascal's principle no longer works because the air starts to compress. But in general, when air meets a wing, it breaks over the top of the wing. And because it gets in a region of space where there is less room, the area that the air has to travel through, the cross-sectional area, gets smaller. Now that happens less on the bottom, because on the bottom, the air doesn't get as close together. Now what this means is that the velocity of the air here, velocity on top of the wing, is faster than the velocity on the bottom of the wing, because these layers of air all meet up back here. So the air that travels over the top of the wing has to travel faster to meet up with the air that's traveling at the bottom of the wing. And that's the part that's have to do with Pascal's principle. The cross-sectional area here is less than the cross-sectional area there, so the air on top has to go faster. That's Pascal's principle. Now, Bernoulli's principle states that because the air is traveling faster over the top of the wing, the pressure on the top of the wing is lower, while the pressure on the bottom of the wing is higher. Well, in physics, pressure is a force over an area. So because the pressure is less on the bottom than on the top, there is a force on the wing this way, from the air pushing at the bottom of the wing towards the area of low pressure. We call this force lift. And the lift force is what pushes an airplane's wing upwards. It is a constant force, and that force is proportional to how fast the air moves over the wing. Now, for you guys who are interested in flight, there are lots of other parts of this conversation that I'm leaving out, like something called angle of attack. The angle of the wing relative to the air makes a difference. And there are things like flaps that can help redirect the air. But flaps allow for you to have short bursts of air being directed downwards. They're not required for sustained flight. Once the plane gets in the air, the lift on the plane is supposed to be equal to the weight of the plane. So the plane travels at neutral buoyancy through the air. It's not buoyancy, but a net force of 0 up and down. And the force acting up is the lift force that occurs because of this change in pressure. Now, planes maintain an altitude by maintaining a speed. If they go faster, the lift force increases on the wing. So believe it or not, in order to, if like say they want to go faster to go from one place to the other because they're behind schedule, which they can do, in order to make sure they don't keep increasing into the air, they have to point the plane down a little bit to counter the fact that they have more lift on the wings. So trimming a plane is the process of changing the angle of attack of the plane so that the upward forces and downward forces stay 0. So that the plane travels at the same altitude the whole time. If you want to land your plane, you just slow it down. It will fall out of the sky. So you slow it down at the right time, and then just before you hit the runway, you deploy the flaps, and there's a cushioning effect that occurs when the air gets trapped under the wings. You've probably felt it before as the plane kind of bounces right before the wheels hit the ground. That's the plane coming down and hitting a cushion of air. That happens because the air gets compressed under the wings of the plane. All right, one more thing. Oop, that's not what I meant. Nope, that's not what I meant. Last try, Mr. Shelton. That's what I meant. All right, so imagine I have a tank of water here. It's got water up near the top. And I punch a hole right there at the bottom. You are not surprised that if I punch a hole at the bottom, the water is going to drain out. Now, just walk with me for a minute on this one. As the water level drops, does the place that the water hits the ground out here stay the same? What happens to that stream of water as the water level drops? Does it go faster or slower? Slower. So we all understand this, that as this water level drops, this will start coming closer to the edge until the water level's at 0. All right. This is a Bernoulli's principle question. I want to talk to you about how we would use Bernoulli's principle for this. Remember, any fluid flowing in a system, Bernoulli's principle is the first thing you should think about. This is fluid that is flowing in the system. Since it is that, the pressure plus the gravitational potential energy plus the kinetic energy at the top of the fluid has to be equal to the pressure plus the gravitational potential energy plus the kinetic energy at the bottom of the fluid. So we're going to set these things equal to each other. Now, this part, just like an example question, but the top and the hole are both exposed to the atmospheric pressure. So the pressure here and the pressure here are the same, right? Atmospheric pressure, what's happening outside, the atmospheric pressure doesn't change that much from, say, the top of this tank to the bottom of this tank. Would you guys agree with that statement? I mean, the atmosphere doesn't change that much. We go way high in the atmosphere maybe, but that's like saying the atmospheric pressure changes from the top of my desk to the floor. Does it? No. So those two pressures would be the same. I'd argue that this is 0 because that's at the bottom. But this H would be however high the surface is from that hole. Does that make sense? Now, you've watched a pool drain. Is the velocity of the water downwards very fast up here? No, I've argued that it's nearly 0. But the velocity down here at the bottom, pretty fast, right? It's flowing out that hole pretty good in the beginning. Let's set these two things equal to each other. So I get pressure plus rho GH plus 1/2 rho 0 squared equals pressure plus rho G0 plus 1/2 rho V bottom squared. Bernoulli's principle. Now, do you notice straight away that the two P's cancel? Because they're the same. And I can get rid of this because that's got a 0 squared in it. I can get rid of this because it's got a 0 in it. What does that leave me with? Rho GH equals 1/2 rho VB squared. Assuming the density of the fluid never changes, we just cancel that out, right? So I solve that for the velocity of the fluid at the bottom, and I get the square root of 2GH. That's got to look familiar to you guys. So if we just rolled a ball down a ramp this high, it would be going the same speed as the water coming out the hole. It all works to be the same. It's the same gravitational force. The same things are acting on it. So in this case, though, it's also pretty clear that as H gets smaller and smaller, the velocity of the water out the hole is going to be less and less. Now, if I'm trying to think about what they're going to do on the AP exam, now that they're introducing Bernoulli's formula and all this to you guys, does it not seem inconceivable that they would just put this on a table? Blue's probably the wrong color for the table. Let's say they put this on a table and ask where that water hits on the ground, right? Can't you kind of see this problem writing itself a bit? I see it. If I wanted to put a new problem on the test and I wanted to include fluid dynamics and I wanted to make sure I also incorporate something else that we've learned this year, this seems like the way to go. You use Bernoulli's principle to figure out how fast the water's going, and then you've got things like the range and the height from the top of the table, stuff like that. Now, you do need to practice and grapple with this, but let me